So, can we say anything about what might have been transmitted? So let's say, in general, errors are far less likely than not errors. Actually, yeah, errors are far less likely than correct transmission. Assuming that, so there are some cases where you can reverse your polarity, in which case errors are much more likely, but let's assume that's not the case here. Let's assume that errors are much less likely than correct transmission. So what is the most likely explanation for this reception? 0, 0, 0, right? Because one error is much less likely than two errors. So, and in fact, in general, if dmin, let's say dmin equals 3, and one error occurs, if dmin is 3 and one error occurs, then there is exactly one code word of distance 1, Hamming distance 1. Actually, let's be a little more formal here. So let's say I send at C, which is in my code. So this is no longer a single parity check code, this is an arbitrary code. Sends a code word, and I receive Y, where the Hamming distance between C and Y is 1. In other words, one error occurred. Yes?
Sorry, a quick question about the previous example. So if you're sending 0, 0, 0 and we're receiving 0, 1, and we have a single parity bit checking, error checking, can we detect this error?
No. So,
just because dmin is...
so here's a good question. This is the repetition code. Yeah. So what does a single parity check code look like if n is 3? So there are 2 free bits and one parity check bit. So how many possible code words?
Like code words would be 4.
4. So let's enumerate them. 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1.
1, 1, 0.
1, 1, 0, you're right. Dmin is 2.
No, that's because dmin is 0.
Yeah. So, in fact, if I send 0, 0, 0, and I get this is a code word. So therefore, I can't detect that error. Okay, anyway. So one error occurred. The Hamming distance between what I received and what I send is 1. So one error must have occurred. Now, in the code, let's say dmin is 3. So in other words, the distance between any 2 code words must be at least 3. So the distance, the Hamming distance between C and Y is 1. So if I have any other code word, C prime, so the distance from C to C prime is 3. So the distance from C to Y is 1. So what's the minimum distance between C prime and Y? 2. It must be 2. So this must be greater than or equal to 2 for any other C prime. So this is sort of the way to think about it. Here is C. Here is C prime. And here is Y. So from C to Y is 1. From Y to C prime is 2. And, excuse me, from C to C prime is 3. So there is an inequality called the triangle inequality, and it applies to all metrics of which the Hamming distance can be shown as 1. And that is the distance from, it's basically the relationship of distances on triangles. So this distance this is obviously the shortest distance between 2 points. So therefore, any path through a different point must have at most, must have at least this distance, because this point, the best case scenario for distance is that this point is on that line. So therefore, this distance plus that distance can be no greater than, can be no less than this, because this is the shortest possible path. So therefore, this must be at least 2. So the distance from C prime to Y must be at least 2. What does that mean? If the Hamming distance is, if the d min is 3, and I have a single error, what can I do? What can I do with Y? Remember, I don't know C at the receiver, all I know is Y. But I look at all my code words and I see, distance from Y to C is 1, distance from Y to anything else is 2 or more. Yes?
You can just assume that you sent C.
That's right. So in fact, assume C was sent. So therefore, 1 error corrected.
So it's pretty much like the example that you showed, that if we have 0, 0, 0 and 1, 1, 1, then we're going to pick 0, 0, 0. Like when the send point is 1, 0, 0, then we're going to pick the bottom.
So you always assume that the most likely explanation for any error event is that the smallest possible number of errors happen. So you always go for an explanation that gives you the minimum number of errors. So in general, okay, let's take a step back. Let's look at this example again. So say I send, actually it doesn't matter what I send, all that matters in the receiver is what I observe. So let's say I observe, we're dealing now with this single parity check code, if this is d min, let's say I observe 0, 0, 1. So I can, has an error occurred? Yes, obviously an error has occurred because this is not in the code. Can I correct that error?
No.
Why not?
Because
yes,
you can differ from 1.
Okay, you say yes, why?
So what is the d min here? Like d min is...
d min is 2.
2.
Okay, just forget about the d min, just look at the code.
Yeah.
So I observe 0, 0, 1. Can an error, I know an error has occurred because this is not in the code.
Yeah.
Can I correct that error?
We could, but we're going to pick 0, 0, 0.
Why?
Because the Hamming distance of 0, 0, 0 is less than 1, 0, 1.
What's the Hamming distance between?
Oh, sorry. Yeah, we could pick either one. Both of them are same. 0, 0, 0 and 1, 0, 1.
Let's actually calculate the Hamming distance to all the code words.
Yeah.
So what's the Hamming distance between these two?
1.
1. What's the Hamming distance between these two?
2.
No.
Sorry, 1.
1.
And that's 1, 2.
Hamming distance between these two, 1. Hamming distance between these two
Is 2.
is
3.
3. So, if the most likely event is that 1 error occurred, but if 1 error occurred, it could be either this one, or this one. So I can't correct that error. I can detect the error, but I can't correct. So d min of 2, and that makes sense. So if 1 error occurs, let's look at my triangle again. If this is 2, then 1 error puts me over here, but 1 additional error can put me at a different code, at a different code word. So in other words, if I'm saying 1 error occurred, I can't distinguish, and I started with Y, I can't distinguish between C and C prime. So therefore, the distance to any neighboring code word must be at least 3. Can we come up with a rule for error correction? So for a code with minimum Hamming distance d min and correct how many errors?
-2.